Very happy to have Roger Varney today as our speaker. And Roger received both his Bachelor of Science and PhD degrees in electrical engineering, electrical and computer engineering from Cornell University. And his thesis research was on photoelectron transport and energy balance in the low latitude ionosphere. He worked with Mike Halley, Dave Heisel, and Charlie Seiler. Sorry. And for the last 2 years, he was a NASA Jack Addy postdoctoral fellow working here at HAO, working with various people here, and has been a project scientist since last August. He's bidding his farewell pretty soon, next month. Since he has not one, but 2 career offers lined up for him, first as a visiting assistant professor at Dartmouth College till June 2015, and then as a research physicist at the Center for Geospace Studies of SRI International. And today he's going to discuss his recent work on ion outflow. Roger?
I'm going to talk about the objectives and design requirements of this model, why write another ionospheric model in the first place. I'm going to talk about a phenomenological treatment of wave-particle interactions that I've introduced into the model to provide some mechanism for generating, non-classical ion outflows. I'm going to show that this model exhibits very interesting interactions between high-latitude convection and the non-thermal ion outflows produced. And I'm going to discuss at length the question of, is outflow really controlled by high-altitude processes or by low-altitude processes? And then lastly, the most exciting part of my talk is going to be the very end, where I'm going to show some preliminary 2-way coupled results, coupling this model with MF-LFM mix. Talk about the setup, some of the preliminary results, and give some recommendations for where I think we're going in the future. Is it working? Yes, good. So, here at NCAR, we do a lot of work with the coupled magnetosphere ionosphere thermosphere model, or CMIT, which is really the marriage of 3 different models. It's the Lyon-Fetter-Mowbray MHD model of the magnetosphere, coupled to the mixed model of high-latitude ionospheric electrodynamics, and the TIGCM, the thermosphere ionosphere electrodynamics general circulation model of the thermosphere ionosphere. So LFM, it's an ideal MHD model of the magnetosphere. I say ideal with an asterisk because it still exhibits magnetic reconnection, and that's not a bug, that's a feature. We want magnetic reconnection to happen in the magnetosphere. We just don't understand all the physics that should set the reconnection rates, so we rely on numerical reconnection to do it for us. The inner boundary of the LFM is a sphere at 2 Earth radii, or 6,370 kilometers altitude. And then a typical grid would extend 30 RE upstream, 300 downstream, and 100 across. Mix is a module for setting the inner boundary conditions on the LFM according to ionospheric electrostatics. So it takes MHD state variables from the LFM and turns them into empirical precipitation. It then takes those precipitation inputs and puts it into an empirical conductance formulation. And then it takes the parallel currents from the LFM and solves the elliptic equation for the ionospheric potential. And then that potential is passed back to the LFM where it sets the electric field at the inner boundary. Now mix actually has 3 different ways to operate it. You can just specify a constant conductance, which is the simplest way to use it. You can rely on the empirical relationships inside of mix to turn the precipitation into conductance. Or you can take the conductance tensors from an external model like the TIGCM, which is the way it's used inside of CMIT. So the TIGCM is a thermosphere ionosphere model. It solves all the neutral thermospheric dynamics as well as the O+ ion transport in the ambipolar diffusion approximation. There are no light ions in standard TIGCM. The electrodynamics in it solve the low and mid latitude wind-driven dynamo, which is then merged with the high latitude potential from mix in a CMIT run. The vertical grid in TIGCM extends from 97 kilometers to the upper pressure level moves around, but it's typically between 500 and 800 kilometers altitude. And here immediately you see what the huge problem is. There's a gigantic gap between the top of the TIGCM and the inner boundary of the LFM. And so the big question, and this is not a unique problem to CMIT, this is a problem that exists in lots and lots of global geospace modeling frameworks. And the question is, what are we missing by having this big gap in the middle of our model? And what we're missing is the possibility for plasma to be transported from the ionosphere out into the magnetosphere, which is a process that we've known happens for a long time. So in the late 60s, the classical polar wind was predicted. The pressure gradient difference between the high latitude ionosphere and these open field lines that go very far down the tail is very drastic. So you can get ion outflows that go out with supersonic speeds quite easily. So here's a calculation from the late 60s showing H plus and HE plus reaching supersonic speeds. These crosses here are the sonic points. They're about at 2,000 kilometers and outflowing from the model. The O plus, however, in this calculation does not outflow. And at realistic ionospheric temperatures, you don't expect the pressure gradients in the ambipolar electric fields to be large enough for O plus to escape gravity. The problem is, we know that it does, because there's lots of oxygen in the magnetosphere, especially during geomagnetically active times. And this has been an enigma for quite a while. So it was first detected, O plus was first detected in the magnetosphere in the 1970s. And since then, there have even been detections of even heavier ions, like NO plus and O2 plus, all of which must be of ionospheric origin. Singly ionized O plus simply doesn't exist in large quantities in the solar wind, so it has to be coming out of the upper atmosphere. But as I mentioned, the gravitational potential energy of an O plus ion is too large for it to be accelerated out by just the ambipolar electric field at realistic ion temperatures. So there has to be something beyond just thermal fluid physics accelerating it out. And a key hint that kinetic processes are responsible for this is that the O plus escape flux is normally observed being carried by non-Maxwellian parts of the distribution function, right? So the picture that has emerged of ion outflow is really kind of a two-step process that looks something like this. You have energy that is input into the high latitude ionosphere, which gets deposited at relatively low altitudes. And there's two major channels for that to happen. The first is you have Poynting flux that is dissipated in the ionosphere thermosphere as Joule heating, generating ion heating and also neutral heating, which produce thermal ion outflow. The other pathway is you have soft precipitating particles that efficiently heat electrons. When you heat the electrons, you increase the ambipolar electric field and you also produce ion outflow. But the ion outflow is produced by either of these pathways typically will not reach escape energy for heavy ions like O+. So there has to be some second step at higher altitude, which I've labeled as wave-particle interactions ? Which turns these thermal ion outflows into non-thermal ion outflows. And the key hint that some kind of wave-particle interaction is going on comes from observations like this of the actual ion distribution functions. So this is an Akebono observation. The axes here are V perpendicular and V parallel. So this is a slice of the distribution function of O+ at 2.5 RE. And you can see it has this characteristic ion conic shape. And these conics are thought to be the result of transverse acceleration followed by mirror force lifting that kind of folds. So if you accelerate ions transversely, you generate like a torus distribution. And then as they go up the field lines, the mirror force kind of bends that torus into kind of this type of shape. Of the different high altitude acceleration mechanisms that have been proposed, you can kind of break them into two different classes. Ones that involve transverse acceleration and one that involve parallel acceleration. And one that gets talked about a lot is ion cyclotron resonance heating. So if you have electromagnetic waves that match the cyclotron frequency of the oxygen, they can efficiently transversely heat that oxygen and produce conic distributions like the one I just showed you. Some other mechanisms, there's a possibility of transverse acceleration by waves that are not at the gyro frequency, but that are at lower frequencies. But if you have multiple waves interacting non-linearly and the frequencies sum to the gyro frequency, that can also be quite efficient. And then there's also this recent this theory that unstable ring beam distributions can be produced by the relative motion between the ions and the neutrals just as they get dragged across the polar cap. In the parallel acceleration category, there are centrifugal forces. So as field lines get dragged across the polar cap, they get whipped around, and that whipping produces a centrifugal force which accelerates things along the field line. The ambipolar electric fields are a source of parallel acceleration, and those fields can be augmented by the presence of superthermal electron populations, like photoelectrons. You can have double layers that form at interaction boundaries between hot and cold electrons. So there's this theory that has been worked on a lot by Barakat and Shunk of if you have hot magnetosheath electrons in contact with cold ionospheric electrons, the two populations shouldn't mix, and instead they should form this electrostatic double layer between them. And when ions get to that double layer, they get accelerated across it. And then lastly, we just know that there are field-aligned potential drops up in the high latitudes because that's what accelerates the auroral particles inwards. If you have an upward field-aligned current region, in order for electrons to carry that current down in the ionosphere, they have to overcome the mirror force which is trying to keep them out. And so a field-aligned potential drop has to form, and this is well described by the well-known Knight relation. Well, the same electric fields that are accelerating electrons into the ionosphere should also be capable of accelerating ions out. So a key theme with everything on the slide, except for the centrifugal forces, is that these are all kinetic theory processes, which is what makes modeling the polar wind with all the relevant physics so daunting. So there are a few so-called generalized polar wind models out there, which are attempts at kinetic models to include a lot of the physics that I've just talked about. And these are typically, they take a fluid ionosphere model up to maybe 1,000, 1,200 kilometers and couple it to a macroscopic particle and cell code at higher altitudes. So a MacPic is basically you take 1 million or so particles, ions, for a given flux tube, and you solve the guiding center equations for each of them, for each ions, and then you can include collisions or wave-particle interactions that's just stochastic kicks on all those various particles. And then in a MacPic, the electrons are still done as a fluid. So you assume a Boltzmannian electrons, and you can have multiple different populations. So two well-known examples of this are the dynamic fluid kinetic model, the DIFE model, and the Utah State University generalized polar wind model. DIFE has only ever been used in 1D. They've only ever done one field line. The Utah group has done collections of field lines so to make a 3D model, but it is fantastically expensive for them to do it. And what makes a first principles description of all of these processes so daunting is that to really describe wave-particle interactions, you would need to resolve waves with periods comparable to the gyro period, so fractions of a second, with wavelengths of only a few tens of kilometers, while simultaneously describing all of the kinetics of a highly non-Maxwellian ion and electron distribution. And no one does this in practice. The models that I just mentioned, yes, they are kinetic models of the ions, but they don't do the waves self-consistently. Typically, they take empirically specified wave amplitudes and use those to drive the wave-particle interactions in the model. So, you know, a first principles description of everything is not practical at this time, nor will it be anytime in the near future. So the existing groups out there that have been experimenting with multi-fluid MHD models of the magnetosphere have all tried various much simpler approaches than trying to describe the first principle physics of all of the ion outflow processes. Mike Wilperger actually just published a nice review paper describing what has been done so far, and I'm going to review some material from that paper. I recommend you read it if you're interested in this kind of ion outflow stuff. The simplest thing that has been done is the method that was introduced by the Winglee group at the University of Washington. And I would call it a ghost cell outflow method. What they do is they go in the ghost cells at the inner boundary of their computational grid, and they populate those ghost cells with fixed densities of H plus and O plus. And then they just allow the centrifugal forces and the pressure gradients and the numerical diffusion in the simulation to pull that fixed density out into the computational domain of the simulation. And even this frankly simplistic approach produces kind of reasonable fluences out into the magnetosphere, and it really does fill up most of the inner magnetosphere with a lot of plasma of ionospheric origin. So these plots showing the density geopause is the surface inside of which most of the plasma came from the Earth, not from the solar wind. And so you can see even with just this ghost cell outflow method, they're getting a lot of plasma out into a significant fraction of the magnetosphere. Another approach, which has been pioneered by the multi-fluid Lionfetter-Mowberry group, particularly at Dartmouth, is to use empirical relationships. So this is a slide courtesy of Bin Zhang summarizing the empirical method that is used. So you go inside the LFM, you take the electric and magnetic fields at 3 RE, so close to the inner boundary. You bandpass filter them to kind of pick out the alphanic portion. And then you compute an alphanic pointing flux. You map that alphanic pointing flux down to 4,000 kilometers is about the altitude of FAST. You then use an empirical relationship which was derived from FAST data to come up with an O plus flux, and then you map that back out and you put that in your inner boundary. Now a problem with this system is that this empirical relationship only gives you flux. But the MHD simulation needs all of the moments, right? It needs density, velocity, temperature. So typically what is done is you fix the velocity and fix the temperature and then turn this empirical flux into an empirical density. To date, the only other group that has tried to put a physics-based ion outflow model is the Space Weather Modeling Framework group at Michigan. And there they've developed a polar wind outflow model, PWOM, which is coupled into their larger framework, kind of as illustrated here. So BATS-RUS is a magnetospheric MHD model. They have an electrodynamics module which plays a similar role to MIX in CMIT. They're taking the potential and the field line currents from their ionospheric electrodynamics model and driving a flux tube model, which then fills the gap region and provides flux back to the BATS-RUS. So PWOM, it's based on a single field line classical polar wind model that was developed in the 1980s. Its bottom boundary is 250, and its upper boundary is, I don't know, 9,000, something like that. It's a Lagrangian horizontal transport model. So they took this single field line model and they just ran a whole bunch of instances of it. So trivially parallelizable independent field lines. It's a classical polar wind model, essentially. It solves the 5-moment equations plus Fourier's law for the heat flows. So this is kind of the simplest set of equations that you can imagine solving for the ionosphere. There's no temperature anisotropy, there's no mirror force, there's no wave-particle interactions, there's no transverse acceleration mechanisms of any kind. But yet, they still get a fair amount of outflow out of this model, even though it is basically a classical polar wind model. And part of the implementation details is that once the ions get into the BATS-RUS, they have no mechanism for coming back. So there's some stuff that kind of, even the upflows that aren't quite at escape velocity, once they make it into the BATS-RUS, they can't come back. And I think that's why they get so much outflow, even though it's just classical polar wind. So these various groups, using wildly different mechanisms for introducing outflow into their models, have nonetheless observed some common results of putting outflow in. And one of those results is a reduction in the cross-polar cap potential with the introduction of heavy ions. This was first mentioned by the Winglee group in 2002. So these curves, the solid curves, are various model runs where the ratio of the O density to the H density in those ghost cells where the density was fixed is ramped up from small to very large. So going through these curves, as you introduce more O into the simulation, you get lower cross-polar cap potential. And adding that extra oxygen actually brings the model down into better agreement with the AMI results for this particular storm run, at least. And this reduction of the cross-polar cap potential with the introduction of O has since been reproduced by multiple other groups. And indeed, I reproduced, and I'm going to show you that later today. Introducing outflow tends to inflate the magnetosphere. So here are some runs that were made using BATS-RUS. The solid lines show the magnetopause, and the dashed lines show the bow shock out in front. The green line is a baseline run, and the blue line is with the PWOM outflow. And the red line is no PWOM outflow, but a ring current model introduced. And you can see the amount of inflation in the magnetosphere with the introduction of outflow is comparable to the amount of inflation that you get by introducing a ring current model. and both of which are significant. And then lastly, outflow tends to affect the substorm dynamics in the tail if it can get to the right spot. So this was one of the very first tests that was done with the multi-fluid Lionfetter-Mowbray model. And this was not with the empirical relationships. It was a much simpler setup where the outflow was just pumped in from a fixed region around the cusp. And in the movie I'm about to show you, the plot on the left shows H plus density from a single fluid run. The other plot shows O plus density from a multi-fluid run. And in both plots, the red lines are field line traces. And what you're going to see happen here, the outflow comes out, that's reconnection in the tail kicking off a substorm. But then in the multi-fluid case, you see a second substorm kicking off, which was not observed in the original simulation. And this second substorm is not observed all the time. It's only if the outflow actually makes it into kind of the right portion of the tail where it can affect the reconnection dynamics back there. Right. Well, in addition to just producing extra substorms, the MFLFM has been observed to actually exhibit what are known as magnetospheric sawtooth oscillations. So this is a plot made by Brambles et al., which was published in Science in 2011, showing magnetic inclination angle from a variety of different runs. This gray line up here is the baseline single fluid run. You can see basically not much is happening. The other runs show these quasi-periodic oscillations, which are basically repeated reconnection events, a sequence of substorms happening with a period of like 2 or 3 hours. And this has been interpreted as a feedback loop involving ion outflow. So when you have a substorm, that inputs energy into the ionosphere. When you put energy into the ionosphere, you generate more ion outflow. That ion outflow goes out to the tail where it then affects the substorm dynamics. And this loop can just repeat ad nauseum. So the various models that I've just shown you clearly have lots and lots of room still for improvement. And that's why I embarked on trying to develop a physically motivated model of ion outflow that could overcome some of the weaknesses of what has been tried thus far. So the model that I'm going to be introducing today, my objectives with it were to span the gap region, make it 3D, cover the whole high latitude ionosphere, include some kind of non-classical O plus acceleration mechanism at high altitude. And that's key to actually getting enough O plus out into the parts of the magnetosphere that I want to. I want this model to be computationally efficient, run no slower than the MFLFM itself, such that I can run it alongside. And I want to make it easily reconfigurable such that I can add or remove different classes of ion outflow relatively easily. And the scientific motivation for doing this is to address which classes of ion outflow has the most significant impacts on the coupled magnetosphere-ionosphere thermosphere dynamics. And to discuss to what extent the effects of ion outflow on the coupled dynamics depend on the mechanism producing the outflow. I don't think that I can make a model that is the end-all, be-all of ion outflow models. I think this is going to be a problem for decades. But if we can answer these questions, we've made a significant step forward. So the model started as a 1D model. The 1D transport is done on a grid from 97 to 8,400 kilometers with variable spacing that increases. The grid points get further apart as you go to higher altitude. The ion transport is done in the 8-moment approximation for H plus, He plus, and ground state O plus. And then I do photochemistry only for a bunch of other ions that have much shorter chemical lifetimes. Now in the 8-moment approximation, I get some of the higher order transport terms like thermal diffusion and the thermoelectric effect, but I do not get anisotropy in that level of approximation. And then the electron transport, the electron density comes from quasi-neutrality, electron velocity comes from parallel divergence of J equals 0. I solve a time-dependent electron energy equation with the thermal conduction term. And then, as usual, the self-consistent ambipolar electric field comes from the small electron mass limit of the electron momentum equation, which is basically just the electron pressure gradient. For the cross-field transport, I've implemented an Eulerian cross-field transport scheme on a grid that is fixed relative to SM coordinates, just like the LFM. So the advantages of doing this is the IPWM grid and the LFM grid are not moving relative to each other. So interpolating from one grid to the other is easy. Just compute the coefficients once and you're done. And I know all the resolutions a priori and everything. The disadvantages to doing it this way compared to like a Lagrangian flux tube scheme like PWOM is you get more cross-field numerical diffusion, and the parallelization is not as trivial. There's more interprocessor communication at each individual time step. The grid is a non-orthogonal magnetic grid. So my grid lines are surfaces of constant altitude, constant L shell, and magnetic local time. I use variable azimuthal resolution going in towards the pole, so I periodically have it as I go inwards to avoid having excessive resolution right at the pole. The pole itself is its own flux tube to avoid the singularity at that point in the grid. The grid that I've sketched here is my so-called single resolution grid, which is only 4 degrees in invariant latitude spacing. That was basically my prototype that ran on my desktop in my office. And the higher resolutions, which is everything I'm going to show you today, have really become my new workhorses. So this model requires a number of external inputs. So I need the ionospheric potential to compute the convection electric field, and I typically take that from mix. I need precipitating number flux and characteristic energy, and I can take that from mix as well. I need neutral densities and temperatures. Everything that I'm going to show you today is simply done with MSIS, but I do have a method for taking those from the TiGCM. And then lastly, I need the neutral winds. And what I'm going to show you today, I'm just ignoring the neutral winds. They're 0. I do have a method to take these from the TiGCM, but it needs more work because TiGCM's magnetic grid is not just a dipole. So in the region where the two models overlap, they actually don't agree on exactly which direction is parallel, which direction is cross field. So here is some baseline results of the model. So what I did was I ran LFM mix with solar wind BZ that was south for 4 hours, and I flipped it north, and then south for another 4 hours. And then I took the mix inputs from that run and drove the IPWM one way. And the two plots I'm going to show you here are the H plus flux and the O plus flux at the upper boundary. And you can see during the southward period, you actually do get a fair amount of O plus flux all the way to the upper boundary, even though I haven't included any extra acceleration mechanisms. And then when it flips north, that pretty much entirely goes away. The classical polar wind still continues. And then when the southward turning comes again, you get more joule heating, you get some more O plus flux again. But if you actually look at the velocities of this O plus flux coming out, they're not at escape energy. So they're leaving the upper boundary of my model and they can't come back because that's how the upper boundary conditions work. But I'm hesitant to really call it outflow. So I wanted to introduce some kind of phenomenological way to put in wave-particle interactions. So what I've done is I've added an extra species to the model, which represents non-thermal O+. And that species obeys a different set of transport equations from the rest of the fluids in the model. And the transport equations that it uses are the simplest set of transport equations that include the combined effects of mirror force lifting and transverse acceleration. So here's a continuity equation, here's a momentum equation. These terms here are your ordinary parallel acceleration terms. So ambipolar electric field, gravity, centrifugal force. And then this orange term here is the mirror force lifting. And then in the energy equation, this term here is transverse heating due to wave-particle interactions. So I need some mechanism for getting particles into this non-thermal population. And so what I've done is I've introduced what I call an ad hoc promotion rate. So it's a quantity in per second. I take the density of thermal ions and multiply it by this quantity, and that's the rate at which ions get promoted from the thermal population into the superthermal population. And there's an equal and opposite term in the thermal continuity equation to ensure that I preserve, number of ions. And then the wave particle heating rate, for now I'm just using a model of ion cyclotron resonance heating based on satellite observations from Bahram et al. 2004. So typically this promotion rate, I only set it to a constant in a fixed region of space. So I just pick a small region and I designate it as my heating region. And I only do the promotion in that region. Nonetheless, when you do things that way, you still get non-thermal ions get pulled out of that heating region and spread all over the polar cap just due to convection. So here's a simple test that I did where I took one potential pattern from mix. And I just said, okay, I'm going to drive the model with this potential pattern, but I'm going to scale it up and down by a scaling factor. And that scaling factor was constant for the first 2 hours and then slowly ramped down, and then I wiggled in a sine wave just to kind of see how the convection coupled into the non-thermal outflows that were produced. So my designated heating region is outlined in white here. It's kind of on the day side. It's kind of like a mock cusp. And what you're going to see, non-thermal ions getting pulled across the polar cap in what kind of looks like a cleft ion fountain. And as you ramp the convection down, this fountain becomes less extended across the polar cap. And as the convection speed varies, it will wiggle back and forth. And this is kind of exactly what we expect to happen with ions accelerated in the clus. The phrase cleft ion fountain was coined in the 80s and has been observed by multiple different satellites. So if you look closer at those runs, you actually notice that there are a number of strong correlations between the convection speed and the properties of the non-thermal outflow. So the top panel here is the non-thermal outflow rate integrated over the whole upper hemisphere of the model. And then the green dashed lines are just that scaling factor to guide your eye. And you can see that the outflow rate is very well correlated with the scaling factor I applied to the potential itself with like a 20-minute time delay. And that can be completely understood in terms of just plasma access to the heating region. So if you look at the rates at which ions enter the heating region, both through the bottom due to upflow from joule heating and also just horizontal transport from the side, those are also well correlated. That's what these other plots are showing. If you also look at the velocities and energies of the particles coming out, they're actually anti-correlated with the convection speed. And that makes complete sense in terms of a dwell time effect. The faster the convection is, the less time particles spend in the heating region, so the less energy they acquire. So in the examples I just showed you, my ad hoc wave particle parameters were just held constant. And yet, the parameters of the outflow that they produced were not constant. They varied a lot with the driving. And so this naturally raises the question of, is ion outflow really controlled at high altitudes or at low altitudes, right? Is what's modulating the heavy ion outflow rate the modulation of the sources of the ion upflow, or the modulation of whatever the source of high altitude free energy that's producing the wave particle interactions? So here are some runs. These were actually done from the ideal storm that was chosen by the GEM outflow focus group. And basically in this ideal storm, it's not really a storm, it's just a 2-hour southward turning. So we did an LFM mix run in which BZ was northward and then southward between 4 and 6 and then flipped northward again. And then I used the mix output from that run to drive the IPWM one way. And the various different lines are different runs with different amounts of promotion. And what I see in every case is a huge burst of upflow with the southward turning. So before the southward turning, yes, there is some outflow coming out, and you get more outflow as you increase the promotion rate, but it's pretty wimpy. And really, it's only after you have a southward turning, you have lots more joule heating that produces ion upflow, that you actually get enough plasma into that heating region for it then to be accelerated outwards. So the bottom plot here is the thermal upflow rate at the lower boundary of my heating region, which is 1900 kilometers in this simulation. And southward turning, you get a huge burst of upflow, and then and only then do you actually get lots of outflow. Yeah. It's similar. So this is actually a lower resolution. These are older slides, so it's actually lower resolution, so it's a big fatter region. But it's still the same kind of idea. It's a designated region on the day side that is just fixed in space. So I took this 4-hour period before the southward turning, and this took the mean outflow rate over that period, and plotted it as a function of the promotion rate. And what you can see is it saturates at some point. So there's a point at which, as you continue to get more and more aggressive with the high altitude acceleration, you reach a point of diminishing returns. You just can't get more outflow. And that's because the outflow is ultimately limited by the upflow from the lower ionosphere. The high altitudes are not very effective at sucking stuff up from the lower altitudes. So even if you evacuate them entirely, you still reach a point at which it becomes flux limited by what the lower ionosphere is willing to supply. So in general, my experience with this phenomenological model is that high altitude acceleration without much low altitude heating can only produce a limited amount of outflow. And conversely, low altitude heating without any high altitude acceleration can accelerate stuff up to the upper boundary, but it doesn't quite reach escape energy. It's not going very fast. But the combination of the two will produce significant outflow. And as I get more and more aggressive with the high altitude acceleration, I get more upflow for a given amount of low altitude heating. And a larger fraction of that upflow becomes outflow. So lastly, I want to talk about some preliminary two-way coupled results. And so everything I'm going to show you basically works like this. You have the multi-fluid LFM model coupled to mix in the ordinary way. Mix is passing to IPWM, the high latitude potential, and the precipitating flux and characteristic energy. And then the IPWM is passing all of the relevant moments of the outflow back to the MF-LFM at the inner boundary. And this is kind of my test simulation that I've just been using as my idealized test bed. The solar wind plasma conditions are constant. 5 per centimeter, minus 400 kilometers per second in the x direction, no wire z velocity, Mach number of 10. I run standalone LFM mix for 4 hours just to set up some reasonable looking initial conditions. And during those 4 hours, I do 2 hours at minus 5 Tesla, 2 hours at plus 5 Tesla, which is kind of a standard way to kind of populate the LFM. I then also initialize the IPWM by running it for 12 hours. 12 hours with the mix parameters from time 4 just held constant. And then from time 4 onwards, I actually run the fully coupled simulation. And so everything I'm going to show you is just after the fully coupled part. And during that fully coupled, I have BZ south for 4 hours, then I flip it north for 2, and then I flip it south again for another 6 hours. So here's a run where I only pass the polar wind H+. So I ignored all the oxygen. I'm just doing 2 fluids in the LFM, the solar wind fluid and the cold ionospheric H+ fluid. This is an XZ plane cut, so the solar wind is coming in from this direction. And this is up, so this is the North Pole, this is the South Pole. And what I'm plotting is the log of the density of the second fluid, the cold ionosphere fluid. And what you're going to see, it comes out, it fills a lot of the magnetosphere. That's a substorm kicking off. And then it kind of settles into this steady magnetospheric convection state. And then that's the northward turning. And then that's the next southward turning. Another substorm kicks off. And then it settles back into another kind of just steady magnetospheric convection state. So this next one, instead of passing the cold H+, I'm just going to pass the cold O+. So this is again a 2 fluid simulation, but it's solar wind fluid and just the polar wind oxygen. And there's no wave particle interactions. And even though this polar wind oxygen is slow, it fills a substantial portion of the magnetosphere. And you can see another substorm kicked off if you look closely. That's the northward turning. And then that's the next southward turning. And you'll see it settle into another kind of SMSC state where the tail is very active. There's not really clear, well-defined substorms. And then lastly, here's a run where I've actually introduced energetic O+. So I did some wave particle heating. In this run, I just did a little bit of wave particle heating everywhere instead of just, and that has the effect of just taking the thermal O+ upflows and kicking them out at higher velocities, so they go further into the magnetosphere. And the fun part in this simulation is to try to count the substorms. So that's clearly one. That's another. That's the northward turning. And then There's the southward turning. That's a substorm. That's a substorm. And that's a substorm. So this simulation that had the energetic O plus exhibited all these extra substorms that weren't observed in any of the other simulations, which is really exciting, right? So this is a comparison of the cross-polar cap potentials from those 3 runs that I just showed you, as well as a single fluid baseline run. And what you can see is there are these oscillations. So the red line is that run with the energetic O plus, and there are these oscillations that appear with a period of about 2 hours in the run with energetic O plus that didn't appear in any of the other runs. Some other things to note, the 2 runs that have O plus in them consistently have lower cross-polar cap potentials than the baseline single fluid run, and that's the Winglee et al. 2002 result that has since been reproduced by lots of other people. And then lastly, the run with polar wind H plus actually has a higher cross-polar cap potential in general than the baseline single fluid run. And that's something that I frankly don't understand yet. Here is the total field line current going into the ionosphere, and it kind of has similar trends to the cross-polar cap potential. So the runs with oxygen have less field line current, and they also have less cross-polar cap potential. That makes sense. This is the hemispheric power, and the clear message from this plot that the outflow is interfering with the precipitation model. So all the runs that I did were with mix run with a constant conductance. And doing that ensures that whatever I end up doing to the precipitation model doesn't feed back to the ionospheric electrodynamics. So unfortunately what's going on here is as I mess with the MHD state variables near the inner boundary, I'm also messing with what gets passed to mix in order for it to compute its empirical precipitation. And in general, the more outflow I put in, the less hemispheric power and the lower characteristic energies I get, which is clearly a bad sign. So this is an area that clearly needs a lot more work, is with the precipitation. That's a mistake. That's a problem that I'm still working on. Right, that's a bug. Right, those are actually the restarts. So there's something clearly wrong. Right, these are preliminary results. These are clear indications of stuff that needs more work. This is the simulated DST from the various runs. And I guess the most exciting thing to note is the run that has the energetic O plus has these periodic dips in DST associated with all those extra substorms. And then this is AE. And I really don't have much to say about AE. The AEs are actually fairly similar across the various runs. So some thoughts on these very preliminary results. Including O plus tends to reduce the cross-polar cap potential, and that's in agreement with lots and lots of other previous studies. Including H plus outflow tends to increase the cross-polar cap potential, and this is a result I still don't understand. And I see these quasi-periodic substorms appear only with the energetic O plus outflow, but not with the cold O plus outflow. And so my thought is that somehow having the faster O plus velocities allows you to get more plasma out into the part of the magnetotail where they will affect reconnection strongly. But this is something that requires a lot more investigation. Clearly there's a lot more future work that needs to be done. I've mentioned the precipitation models that need to be worked on so that we don't interfere with them by introducing outflow. We also need a way to kind of regulate the wave-particle interactions. So I've introduced a way to kind of capture them phenomenologically, but I really don't have any set of rules for regulating them in a causal fashion. And so what I envision doing in the future would look something like this. Bin Zhang has developed a cusp identification algorithm. So if a field line lies in the cusp as identified by that algorithm, do wave-particle interactions with a set of cusp rules. Otherwise, if the alphanic pointing flux exceeds some kind of threshold, then you can say, okay, that's an auroral field line, because it's not in the cusp, but it has lots of alphanic pointing flux. So do wave-particle interactions according to another set of auroral rules. And then, if neither of these are true, then just treat it like a polar cap field line. Either do nothing or do like a little bit of wave-particle interaction or something like that. But this is clearly something that needs a lot more work. And The trickiest part is going to be trying to look at the literature of satellite observations and come up with something vaguely reasonable for these various sets of rules. And that's going to be a big challenge for the future, for sure. That's all I have. Thanks a lot for coming.
So questions?
I don't know, I can't remember which slide it was, but there was when you showed the polar wind O+ outflow and then subsequently the WPI induced outflow. And the density of the polar wind O+ outflow looked pretty substantial to me, despite the fact that you were saying earlier that there's just not enough energy to get much O+ out. So what's going on there?
Good question. Good question. So the experience of the Michigan group has been, even though PWOM only has classical polar wind, once that gets out to the inner boundary, there's still enough centrifugal forces to throw it everywhere, right? So essentially, what I'm seeing must be the same deal. That this O+ that I'm pumping, even though it's cold, even though it's slow, there's enough centrifugal forces to spread it around. Yeah, I mean, that more analysis needs to be done. I need to actually write all the routines to compute all the flux integrals, so I can do fluxes through various shells and actually do quantitative comparisons instead of just squinting and wondering how the color bar is set, right? So yeah, that's a great question that deserves further investigation.
And if I could just ask a technique question. So this was on slide 21, but you were forcing del parallel dot J equals 0 in those standalone runs. Did you relax that in the coupled model because you got field line currents floating around there?
Right. So I'm actually not using the field line currents from mix at the moment. So if you take a field line current, you enforce del parallel equals 0 with a specified field line current, but you ignore that that field line current is being carried by a beam of energetic electrons, you end up getting a spurious answer, which is not what I wanted to do. So yeah, this is work for the future, is actually coming up with the electron velocities correctly, accounting for the field line currents and for which populations are actually carrying those field line currents. And that's tricky to do because you have to do the superthermal part of it right.
Thank you.
Mary?
For the webcast.
So it looks like you're getting Sawtooth oscillations when you put in energetic O+. And so my question was just, I don't know Brambles at all as well as the other guy does. So was that also energetic O+ in the Brambles?
Yes.
So you're both getting a similar result from including energetic O+.
So where is my Brambles slide? Right, so actually, this slide, what is done is the empirical relationship only gives you flux. So you have to guess the energy and velocity. Typical guesses are like 40 kilometers per second and 100 eV, which is around the same ballpark that I get out of the top of the model when I do wave-particle interactions. The cold polar wind O+ outflow will typically be like 1/4 to 1/2 an EV in temperature and have a parallel velocity of maybe like 2 or 3 kilometers per second. And if you look at the subsequent Brambles work that was done kind of exploring the parameter space, the range of velocities and energies that they explore and see Sawtooth with all of them are all kind of in the range that I would call energetic. Yeah.
Would you find the substorm-like oscillations toward the end of your simulation with the O+? Do you have a sense for what is responsible for the periodicity you get? Is it related to the outflow velocity or?
So I haven't done enough analysis work to answer that in my simulations. For the Sawtooth that have been produced by Brambles et al., basically the periodicity comes from the time it takes plasma to travel from the ionosphere out to the X line in the tail. So you know, an hour or two is kind of the time scale it takes to go 20 RE down tail. And there's also a time delay involved in you input energy into the ionosphere, and then that has to heat stuff and get stuff. But that time delay is on the order of like 10, 15 minutes. It's really the travel down the tail that is the largest part of the time delay in that feedback loop.
It looks like in your preliminary work you have a nice symmetric situation in terms of your north-south cusp. Do you have any sense of what happens when you get the summer-winter dipole tilt?
Right. So I didn't mention this. Everything that I'm doing in the stuff that I showed you in these idealized simulations is no dipole tilt, and I only run one instance of the IPWM, and then I take so I run the northern hemisphere, and then I just assume the southern hemisphere is the mirror image. A step down the line, for sure, is exploring hemispheric asymmetry, and that will happen after we've debugged all the stuff in what we have now. But
So
that's something we intend to do, for sure.
What is the top boundary condition for your model, and how sensitive you result to the top boundary condition? And when you couple with FM, the lower boundary of FM and the top boundary is matched, or how consistent between the two models?
So right now, my upper boundary is actually beyond the inner boundary of the LFM. It's at like 8,400 kilometers. And my conditions there are basically just zero derivative on the fluxes, so stuff just goes. For the light ions, that's fine. For the heavy ions, if they're flowing out, I allow them to flow out, but I don't allow them to flow back in. So it's kind of like a one-way outflow but not inflow condition. I have done tests where I have moved that upper boundary up and down, and the results below 3,000 kilometers are very insensitive to whether that upper boundary is at 6,000 or 8,000 kilometers, which is reassuring, which is good. Right now, what I'm doing is I find where the first computational cell of the LFM is in my grid, and I interpolate onto there, and I pass that into the first cell. So I'm doing the same thing that Oliver Brambles did in actually modifying the first active cell of the LFM. And other ways to do those inner boundary conditions are something that one of Bill's students is working on right now. So right now, it is not self-consistent in that I pass stuff one way, but there's no communication backwards. And the way PWOM is coupled to BATS or US is actually done the same way. So I've actually talked with Alex Glosser about this issue. And he said, oh yeah, if you try to couple it back, it's guaranteed to be unstable. You're never going to get it to work. So with the light ion outflows, they're actually supersonic. So their characteristics all point upwards. So there really shouldn't be communication backwards anyway. The only thing that might have communication in two ways are the cold O+, which is not supersonic. And maybe down the line we could develop some kind of nudging scheme where we take the portion of my grid that overhangs into the LFM portion and kind of nudge it towards the LFM to try to get communication flowing in both ways. That's something to think about. That's kind of a complicated project.
Maybe an ignorant question. So the wave particle interaction is not important for H+, only for O+?
It can affect H+, but it's not really needed, right? So once the H+ reaches supersonic velocities, right, if you accelerate it more, what you see is the velocities go up and the densities go down such that the flux is still preserved, right? So yes, if you have stuff that matches the H+ cyclotron frequency, which is faster than the O+ cyclotron frequency, they will transverse heat them and accelerate them, for sure. But that process doesn't really affect the amount of flux that you get out of the ionosphere, because there's already enough to get it to supersonic speeds, the light ions to supersonic speeds, and once they're up there, who cares how much more you accelerate them? They're gone. They're escaping.
So one of the things that you can do with a two-way coupled model like this that I don't think anybody's ever done is ask, what does the coupling do to the ionosphere? I mean, you showed diagnostics for the magnetosphere. It'd be interesting to see how, what the substorm process, this periodic substorms and so on, how it's manifesting itself in the ionospheric properties.
Right. So what happened in the Bramble simulations are you have a substorm that generates lots of alphanic pointing flux going back towards the planet. And then alphanic pointing flux near the inner boundary is used as a proxy for Joule heating ion upflow, which then produces more outflow. In these simulations, we can actually see the substorm create Joule heating, modify the F region, change the transport, and do all the self-consistent. So we can ask, does the ionosphere ever get worn out, right? Does it ever actually run out of, right? Does it get depleted to the point where it can't recover? So one thing that I showed but I didn't comment on was in, where's this movie? Oh yeah. Nope, not what I wanted to do. So in my baseline results movie, which should be in the background here. So get me out of this. Right. During the first southward turning, you see a lot more O plus outflow than you see during the second. And that's because this 2 hours of north is not nearly long enough for the topside ionosphere to recover from that first southward turning. So yes, the ionosphere, the topside ionosphere, should exhibit large amounts of memory, should exhibit hysteresis, and we can start to actually probe at what that is actually doing, and ask,
Precipitation, you'd be making O plus all the time.
Right. Right. The question is, the precipitation is making it at low altitudes, right? Right. And so the question is, how fast is that transported up to the high altitudes? How long do the high altitudes really take to recover? So you're absolutely right for the F region, right? The precipitation is going to replenish everything, right? And the precipitation from every time you have a substorm, you should make lots of it, right? I'm not really sure what the topside should do. So it's a good question.
But I think, by the same token, that once you get enough, once you dial up the wave-particle interaction enough, the supply of cold plasma is regulating the flow to the magnetosphere. I think you're saying that the converse of that is that the ionospheric response is going to be weakly dependent on all this wave-particle interaction stuff.
I think you're right.
Because all you need to do is get the cold plasma up to several thousand kilometers, and from the ionospheric's perspective, it's gone.
Right.
So regardless of the resolution of all of these acceleration mechanisms, we have at least enough to understand how topside O plus, how topside ionosphere is going to respond to these depletion events.
What's determining the supply from the lower ionosphere is the Joule heating, right? And if the outflow out in the magnetosphere is modifying the field line currents, is changing reconnection rates, is producing extra substorms, you're changing the Joule heating. And so that's where the feedback would happen.
No more questions. So let's thank Roger again.
Thank you.